Hello students, welcome to EPG Pathshala. Today we shall be studying the first module of our paper Remote Sensing and GIS Applications in Environmental Management. In this module we shall be studying two broad topics. First one is the concept of space and time, and the second one is the types of satellites. So, at the end of this module you would be able to appreciate the fact how space and time provide an important framework for spatial analysis related problems and providing effective solutions to those problems. You would also be able to appreciate the fact how spatial information adds to the abundance of information already present and providing a better decision making process. So, dear students, coming to the first topic of the concept of space and time. The concept of space can be related to the concept of geo in geography, which refers to geographical entities, that is physical features, and phenomena, that is processes. The geographical entities vary over scale, ranging from a small house to the entire planet itself. The phenomena occurs at varied spatial scales and changes over a period of time. Thus, geographical phenomena encompass the concept of both space and time. The real world that we talk about is the physical environment around us that we perceive according to the five senses, that is sight, touch, taste, smell or hearing. Real world phenomena may be natural or it may be man-made. So, any process that takes place without any human intervention is a natural phenomena such as topography, weather, natural disasters, while those which require human intervention are man-made processes. For example, the construction activities, industrial processes and so on. So, everything in the world has a spatial dimension or pattern. For example, location of ATM in a city, telephone directories, maps, locations of civic amenities, travel route to workplace, picnic destinations and many more can be added to this list. So, the perception of the world around us falls in the domain of spatial cognition, that is a field that explores the spatial properties of the world and its changes over time. Coming to the properties of space, the first and the most important property of any space is location. So, every object in a space can be characterized by its location. Location exemplifies spatial data, implying that it is in some way reference to locations on the earth. This location may be represented by Cartesian geometry, that is xy plane, or geographical coordinates, that is latitudes and longitudes. Further, the location of an object can provide answers to various questions such as where, next to what, close to or how far from another object, and it may be answered in terms of latitude, longitude, precise address or in relation to other object. The precise location that is based on the latitude and longitude of a place is called as its absolute location, while a location defined on the basis of a frame of reference or on the basis of a place whose absolute location is known is called as relative location. The next property of space is size. Size refers to the geometric dimensions of any object in space. Further, size also involves the concept of relative size rather than absolute size, thus emphasizing the concept of scale. Any object on a large scale will provide higher detail about the object or area under investigation, while that in a small scale will provide lesser details, but it will cover larger area on the ground. So, coming to the first subtopic, that is scale. Scale represents the relationship of the distance on the map or data to the actual distance on the ground. So, map detail is determined by the source scale of the data, that is the finer the scale, the more detail would be observed. Source scale is the scale of the data source. It may be aerial photo or a satellite image from which the data is digitized, may be into boundaries, roads, land covers, etc. in a GIS domain. For example, this figure shows the spatial scale of a wetland. Spatial scale in general involves grain and extent, Grain, it is the size of your pixel and the smallest resolvable unit, while the extent is the size of the study area and the largest resolvable unit. This picture shows a section of a wetland and it progressively gets bigger in grain sizes. The more the details, the better. However, more detail requires more computer power. We can also make the grain size larger, but we can never make it smaller. So, in this table, we will see how varied levels of scale are used at various levels of planning and exercises, and the information contents on the base map and thematic maps that are used for these planning exercises. The first one being regional planning boundaries. In this, the range of the scale may be from 1:50,000 to 1:1 lakh to 1:2 lakh 50,000 to 1:10 lakhs. In general, the information content is national boundaries, roads, railway lines, bridges, water bodies such as rivers, canals, topography and natural hazard prone areas, besides ecologically and environmentally sensitive areas and wetlands. The second category is of perspective planning. In this, the range of scale of maps varies from 1:50,000 to 1:1 lakh to 1:2 lakhs 50,000. This involves metropolitan boundaries, roads, railway lines, bridges, rivers, canals, lakes, marshy lands, ponds, embankments, low-lying areas, and it also includes religious places, places of archaeological and historical interest, city forests and parks, green belts, cantonment areas, floodable areas, sanitary landfill sites, and environmental and ecologically sensitive areas. Next category is of development planning, which includes the scales of 1:10,000, 1:25,000 and 1:50,000. This information content is the same as the perspective planning. Besides, it also includes ward-wise population and density distribution, water supply and sewage disposal networks, gas and electric supply works and lines, parking sites, slums and squatter areas, and the areas that limit the development in general. The next is annual planning, which includes the scale of 1:5,000, 1:10,000 and 1:25,000. All information contents are the same as in development planning except for larger details. The last category is the projects or schemes or site planning. This can be done at the scale of 1:5,000, 1:1,000, 1:2,500 and 1:5,000. It generally includes all vegetations that may comprise of trees, bushes, arboriculture, etc., water bodies, high tension or overhead electric and telephone lines, water supply lines, sewer lines including manholes and drainage channels. You would notice in this table, as we proceed from regional planning boundaries to the projects and schemes or site planning, the scale continuously keeps on moving from small to larger scale. So does the details increase maybe from national boundaries to individual city or town levels. The next category that includes the property of space is resolution. Resolution refers to the size of the smallest possible features that can be detected. Most remote sensing images are composed of a matrix of picture elements or pixels, which are the smallest units of an image. Image pixels are normally square and represent a certain area on an image. It is important to distinguish between pixel size and spatial resolution. They are not interchangeable. For example, if a sensor has a spatial resolution of 20 meters and an image from that sensor is displayed at full resolution, each pixel represents an area of 20 meter to 20 meter on the ground. In this case, the pixel size and resolution are the same. However, it is possible to display an image with a pixel size different than the resolution. For example, many posters of satellite images in hard copy have their pixels averaged to represent larger areas, although the original spatial resolution of the sensor that collected the imagery remains the same. Coming to the types of resolution, in general there are 4 types of resolution: spatial, spectral, radiometric and temporal. The first one is spatial resolution, which is the measure of smallest angular or linear separation between two objects that can be resolved. Spectral resolution includes the number and width of wavelength intervals or spectral bands. Radiometric resolution implies the sensitivity to differences in radiance or the number of brightness levels. Temporal resolution refers to the time interval between data acquisitions. We shall study each of these in detail. The first one is the spatial resolution. As I already said, it is a measure of the smallest angular or linear separation between two objects that can be resolved. Refer to the figure shown on the left hand side. Spatial resolution of a sensor depends primarily on the instantaneous field of view. If you can relate to the figure, the instantaneous field of view is the angular cone of visibility of the sensor and determines the area on the earth's surface which is seen from a given altitude at one particular moment in time. The size of the area that is viewed is determined by multiplying the instantaneous field of view by the distance from the ground to the sensor, that is the altitude. This area on the ground is called as the resolution cell and determines a sensor's maximum spatial resolution. So, images where only large features are visible are said to have coarse or low resolution, as you can see in the upper figure. Examples include commercial satellites that provide imagery with resolutions varying from a few meters to several kilometers. The second figure shows the example of fine resolution, in which the images that have fine or high resolution, in that even the small objects can be detected. Examples include military sensors, which are designed to view as much detail as possible and therefore have very fine resolution. Generally speaking, the finer the resolution, the less total ground area can be seen. Figure shows the comparison of spatial resolutions at different levels at 1.5 meters, at 4.5 meters, at 13.5 meters and 40 meters. As you can see, as we move from 1.5 meters to 40 meters, the resolution decreases from finer to coarser and the image becomes blurred at coarser resolutions. Okay. The next is spectral resolution. The importance of spectral resolution can be understood from the fact that different classes of features and details in an image can often be distinguished by comparing their responses over distinct wavelength ranges. Broad classes such as water and vegetation can usually be separated using very broad wavelength ranges, for example, the visible and near infrared. Other more specific classes such as different rock types may not be easily distinguishable using either of these broad wavelength ranges and would require comparison at much finer wavelength ranges to separate them. Thus, we would require a sensor with higher spectral resolution. So, all in all, spectral resolution describes the ability of a sensor to define fine wavelength intervals. It depends on the number and width of wavelength intervals or spectral bands. The finer the spectral resolution, the narrower the wavelength range for a particular channel or band. For example, this figure shows the two types of resolution, low spectral resolution and high spectral resolution. As you can see, in the low resolution, the bands are much wider and they encompass a broad range of wavelength range, while if we have narrower wavelength bands, then we can distinguish easily between subtypes of narrow bands that would have been incorporated in the wider bands. An example is a hyperspectral data that has a large number of contiguous very narrow bands that enable deriving a complete and detailed spectrum. So, it is this hyperspectral data is supposed to have very high spectral resolution. The next one is radiometric resolution, which implies sensitivity to differences in radiance or the number of brightness levels in an image. For example, if we have a 1-bit data that represents the radiometric resolution, then the values that can be differentiated would be 2 raised to the power 1, that is 2, or you will have 2 shades, that is black and white. However, as we move to higher bits of data, then we can have increasing gray levels between black and white. More the number of gray levels, more would be the radiometric resolution. The last resolution is the temporal resolution, which is defined as the amount of time needed to revisit and acquire data for the exact same location. When applied to remote sensing, this amount of time depends on the orbital characteristics of the sensor platform as well as sensor characteristics. The temporal resolution is high when the revisiting delay is low and vice versa. Temporal resolution may vary from hours to days and is usually expressed in days. Spectral characteristic of features over the surface of Earth may change over time, but these changes can be detected by collecting and comparing multitemporal images. For example, during the growing season, most species of vegetation are in a continual state of change, and our ability to monitor those subtle changes using remote sensing is dependent on when and how frequently we collect imagery. By imaging on a continuing basis at different times, we are able to monitor the changes that take place on the Earth's surface, whether they are naturally occurring, such as changes in natural vegetation cover or flooding, or induced by humans, for example, urban development or deforestation. This is an example of a multitemporal imagery where the same place has been the data for the same place has been acquired at different time scales. So, after studying both scale and resolution, we need to know how are the scale and resolution related. Okay. So, the first is digital number values. Like I said, any image is made up of picture elements. So, these picture elements, depending on their brightness, have certain numerical values. Those are called as digital number values. These are generally recorded using 8, 9 or 10 bit binary computer coding scales, and we also studied that spatial resolution is the measure of smallest angular or linear separation between two objects. So, after this, if we talk about scale, scale is the geographical coverage of an image. It may be the ratio of image distance to ground distance. So, large versus small spatial scale and how coarse versus fine spatial resolution are related to each other, this we will see in the coming figure. In this figure, on x axis we have resolution that changes from coarse to fine, while scale that changes from small to large. So, as we move from coarse to fine, our scale changes from small to large. For example, on coarser side we have images of AVHRR, that is advanced very high resolution radiometer, and moderate resolution imaging spectroradiometer. Higher resolution includes Landsat imagery that has resolution at 30 meter, 60 meter and thermal bands at 90 meter. Still higher is high resolution satellite imagery such as GeoEye and Iconos, and the highest resolution, that is the most finest resolution, is obtained for aerial photos and digital images, which are in general large scale images. Another factor while determining the space properties is accuracy and precision. While defining any spatial data, we need to know how does accuracy and precision differ. So, accuracy is the degree to which information on a map or in a digital database matches true or accepted values. Thus, data accuracy is a statement of how closely a bit of data represents the real world. So, accuracy conceptually includes statistical methods of uncertainty and variation, as well as how and when the information was collected. Spatial data accuracy is independent of map scale and display scale and should be stated in ground measurement units. So, coming to precision, which is quite different from accuracy. Precision refers to the level of measurement and exactness of description in a database. The last property, in fact the two last properties about space that we will discuss here is distance and direction. Distance refers to the length between two objects in space. It has a linear dimension that is measured in terms of maybe kilometers, meters or any subunits of meters. Distance generally provides answers to questions such as how far, how near and so on. When the distance is measured in the smallest terms between two objects, it becomes displacement. Direction. When the concept of angle is included in defining the location of an object in space, it is called as direction. It is generally measured in degrees or in radians and is useful in defining as to one object may lie in what direction to the other object. So, after studying the concept of space, properties of space, the next topic is models. So, first we need to know what are models. In general, models are the abstract representation of real world phenomena. For example, if we talk about globe is a physical model of the earth. If we talk about weather forecasting models, they are generally simulation models that are used to predict the weather conditions of a area. Various disciplines have tried to develop tools and techniques to provide answers that are pertaining to objects and processes in space through the spatial and temporal analysis of data about geographical entities and phenomena. Quite a many of these concepts have been incorporated in geospatial studies by means of static and dynamic models. Often, the most useful of these applications have to do with the complex interactions between relatively static geographical entities and the dynamic phenomena through which these entities themselves evolve. They also involve the notion of space and time. While the notion of space involves the answers to questions such as where, that of time involves the answer to the question of when. After this, coming to our second subtopic of the module, which is the types of satellites. So, a satellite is any object, man-made or natural, that revolves around a planet in a circular or elliptical path. Moon is the only natural satellite of the earth. Here we shall be talking about the artificial satellites. Based on its applications in general, we have satellites of the following types. They may be weather satellites, communication satellites, scientific satellites, navigational satellites, military satellites and Earth observation satellites. The first one is weather satellites. Weather satellites help in predicting the weather of a place or a region and are of significant interest to meteorologists for weather forecasting. Typical weather satellites include the TIROS, that is television infrared observational satellite, COSMOS and GOES, that is geostationary operational environmental satellites. With the advent of space missions of India in 1970s, India launched its weather satellites with assistance from Soviet Union. These satellites include Aryabhatta. This was the first satellite that was launched on April 19, 1975 from Kapustin Missile and Space Complex using Inter-Cosmos 2 launch vehicle with a period of 96.5 minutes. The decay date of the satellite was 11th February 1992. The satellite provided data in the field of space physics and earth sciences. The next satellite is Bhaskar Sega 1, which was launched on 7th June 1979 from Kapustin Yar Missile and Space Complex using modified SS-5 SKN IRBM plus upper stage launch vehicle with a period of 95.2 minutes. The decay date of the satellite was 17th February 1989. The satellite provided data in the disciplines of astronomy, communications, engineering and earth sciences. The next in the series is Rohini Satellite. Rohini technology payload was the first one, which was an experimental satellite with a payload of 35 kg launched on 10th August 1979 from Satish Dhawan Space Center, Sriharikota, Andhra Pradesh. This satellite was intended for measuring in-flight performance of first experimental flight of SLV-3, the first Indian launch vehicle. However, it did not achieve its orbit. Rohini RS-1 with a payload of 35 kg was launched on 10th August 1979 from Satish Dhawan Space Center, Sriharikota. This was India's first indigenous satellite launch and used for measuring in-flight performance of second experimental launch of SLV-3. The launch of Rohini RS-1 made India the seventh nation to possess the capability to launch its own satellites on its own rockets. The decay date was 20th May 1981. The next satellite is Rohini RS-J1, which was used for conducting remote sensing technology studies using a landmark sensor payload. It was launched on 31st May 1981 from Satish Dhawan Space Center with a payload of 35 kg. The decay date was 8th June 1981. After weather satellites, we shall study some of the communication satellites. These satellites find their applications in transmission of TV and radio signals through the satellite. Examples include Telstra and Intelsat. So, Telstar is an international collaboration between AT&T, Bell Labs, National Aeronautics and Space Administration, that is NASA of USA, French National Post, Telegraph and Telecom Office of France, and British Broadcasting Agency, that is British General Post Office. The satellite was launched on a Delta rocket on 10th July 1962. It is the world's first active communication satellite, enabling the broadcasting of television signals, telephone calls and fax images through space. Telstar 1 was placed in low Earth orbit with a period of 2.5 hours to provide signals. So, communication satellites of India include INSAT and Apple. India launched its first experimental communication satellite Apple on 19th June 1981 with a payload of 670 kg. INSAT 1A was the first multipurpose communication satellite and meteorological satellite that was procured from USA. However, it worked only for 6 months. INSAT 1B was launched on 1st June 1983, which was identical to INSAT A and served for more than the design life of 7 years. Both INSAT 1A and INSAT 1B was launched from Air Force Eastern Test Range, Florida. The third category is the scientific satellites. These perform a variety of scientific missions such as Hubble Space Telescope and Hitain Scientific. In India, examples include AstroSat, Mars Orbiter Mission and Chandrayaan. AstroSat is the first dedicated Indian astronomy mission aimed at studying celestial sources in X-ray, optical and ultraviolet spectral bands simultaneously. The payloads cover the energy bands of ultraviolet, that is near and far, limited optical and X-ray regime from 0.3 kilo electron volts to 100 keV. It enables the simultaneous multi-wavelength observations of various astronomical objects with a single satellite. AstroSat, with a lift-off mass of 1515 kg, was launched on September 28, 2015 into a 650 km orbit by Polar Satellite Launch Vehicle C-30 from Satish Dhawan Space Center, Sriharikota. The minimum useful life of the AstroSat mission is expected to be 5 years. The next one is Mars Orbiter Mission, which is ISRO's first interplanetary mission to planet Mars with an orbiter craft designed to orbit Mars in an elliptical orbit of 372 km by 80,000 km. Mars Orbiter Mission can be termed as a challenging technological mission considering the critical mission operations and stringent requirements on propulsion, communications and other bus systems of the spacecraft. The primary driving technological objective of the mission is to design and realize a spacecraft with a capability to perform Earth-bound maneuvers, that is EBM, Martian transfer trajectory MTT and Mars orbit insertion phases and the related deep space mission planning and communication management at a distance of nearly 400 million kilometers. Autonomous fault detection and recovery also become vital for the mission. The next in the series is Chandrayaan, which has Chandrayaan 1 and 2. Chandrayaan 1 is India's first mission to moon, which was launched successfully on October 22, 2008 from Satish Dhawan Space Center. This spacecraft was orbiting around the moon at a height of 100 kilometers from the lunar surface for chemical, mineralogical and photogeologic mapping of the moon. The spacecraft carried 11 scientific instruments built in India, USA, UK, Germany, Sweden and Bulgaria. Chandrayaan 2 is an advanced version of the previous Chandrayaan 1 mission to moon. It is configured as a two-module system comprising of an orbiter craft module and a lander craft module carrying the rover developed by Indian Space Research Organization. Navigational satellites help in navigation of vehicles, ships and planes. Typical examples include Navstar GPS, that is Navigational Satellite Timing and Ranging Global Positioning System, developed by US Department of Defense and later released for civilian purposes. Besides USA, Russia, China, European Space Agency and India have their own navigational satellite systems. The navigational satellite system of India is known as IRNSS, that is Indian Regional Navigational Satellite System, which is a constellation of 7 satellites. The last one of these satellites was launched on April 28, 2016. The next category is of military satellites. These satellites find applications in defense and intelligence services for military strengthening. Some of the examples include Cosmos, SkyMed, ELISA, RISAT, OptSat 3000, etc. In India, GSAT-7 Rukmini was the first military communication satellite developed by ISRO for Indian Defence Forces, with the Indian Navy being its primary user. Rukmini was launched early on August 30, 2013 atop an Ariane 5 ECA rocket from Kourou in French Guiana. Rukmini was successfully placed into a geosynchronous orbit at around 36,000 kilometers above the Earth. This gave India a major push in maritime security, and Rukmini is also the last of ISRO's 7th 4th generational satellites. The last category among the type based on applications is the Earth observation satellites. These satellites observe the planet Earth for mapping, detecting and studying the changes, as well as have a variety of other environmental applications. In general, satellites are placed in one of the 3 types of orbits around the Earth. Geostationary, that is the motion of satellite is aligned with the motion of the Earth. Polar or sun synchronous, that is it is synchronized with the sun. The type of orbit determines the design of the sensor, its altitude with respect to the Earth and its instantaneous field of view, that is the area on the Earth, which can be viewed at any particular moment in time. Examples in India include Indian remote sensing series of 1A, 1B, 1C and 1D, OceanSat, ResourceSat and Cartosat series of satellite data. So, dear students, to summarize, I hope at the end of this module you would be able to understand the conceptual framework of space as well as time. You would also be able to appreciate the various properties of space that we have discussed in this module, such as distance, direction, size, shape and so on. I also hope that you would be able to understand how models are useful in providing spatial and temporal solutions to problems, and you would also be able to appreciate the various types of satellites that we have discussed in this module, be it the weather satellites, communication satellites, military satellites or scientific satellites or Earth observation satellites. We shall study more about these type of satellites in the coming modules. However, I hope I have been able to provide a general overview of the types of satellites in this module. Further, this module shall be helpful for you for laying the basic foundation of studying about the geospatial technology in detail in the coming modules, be it remote sensing, geographical information system, that is GIS, and geographical positioning system, that global positioning system, that is GPS. I hope you all would be benefited from this module. Thank you.